Points of inflection. There is another type of important point that a curve may possess. This is called a point of inflection. A point of inflection is a point on a curve at which the curve goes from being concave upwards to concave downwards, or vice versa. So here's an example of one of those points. So we can see that the curve is concave downwards, and then it goes to being concave upwards. So the point at which it changes is known as the point of inflection. From the slope of the curve dy dx equals f prime x drawn directly underneath, so here's the derivative of this curve, we can see that the slope curve must have a turning point at D, which has the same x-coordinate as C. So this is the point D on our U-shaped graph, our quadratic function, and we know that this quadratic function is the derivative of this cubic function. So this is the point of inflection on our cubic function, and it has the same x value as the minimum point, which is a turning point, on our quadratic curve, which is the derivative. For this to be the case, we need the slope of the slope, d squared y dx squared, which is the second derivative, to go from negative to 0 to positive, or from positive to 0 to negative. So in this case, we have a negative slope, we're going downwards, it's less than 0. Then we have a slope of 0. And then we have a positive slope, it's going upwards, it's greater than 0. Put another way, for the curve y equals f of x to have a point of inflection at C, so a point of inflection at C, the second derivative, d squared y dx squared, must be 0 at C and change sign about C. So change sign either side of C. So either going from negative to 0 to positive, or positive to 0 to negative. So point of inflection. The curve y equals f of x has a point of inflection at C, x1, y1, if d squared y dx squared is equal to 0 at C, so the second derivative is equal to 0 at C, and d squared y dx squared, the second derivative, changes sign at C. To investigate if d squared y dx squared, the second derivative, changes sign at a point, we take sample x values, one on each side of the point, and by examining the signs of the second derivative with these values of x, we see if there is a change of sign. Example, find any points of inflection on the curve y equals the natural log of x squared plus 1, which is defined for all x values elements of the real number set. So we have y equals the natural log of x squared plus 1. So the first thing we want to do is differentiate. So we're going to use the chain rule. So we differentiate the outside. So we're going to differentiate the log. So the natural log becomes 1 over x squared plus 1. And we multiply that by the derivative of the value, or the inside function. So we differentiate inside, and the x squared becomes 2x. So the derivative dy dx is equal to 1 over x squared plus 1 multiplied by 2x. So we used the chain rule here. And 1 times 2x is 2x, and that's all over x squared plus 1. So here we have the first derivative. Now we want to find the second derivative. And since this is a fraction, we use the quotient rule. So this is the u, and this is the v. So our formula is v du dx minus u dv dx all over v squared. So d squared y dx squared is going to be x squared plus 1 multiplied by 2, which is the derivative of u, minus 2x multiplied by 2x, which is the derivative of v. And that's all over x squared plus 1 squared. So next we multiply out our brackets. So d squared y dx squared equals 2x squared plus 2 minus 4x squared, and that's all over x squared plus 1 squared. And then simplifying, we get minus 2x squared plus 2 all over x squared plus 1 squared. So now we put d squared y dx squared equal to 0, we put the second derivative equal to 0. Since this is the second derivative, we put it equal to 0. And then we solve for x. So multiplying both sides by x squared plus 1 squared, we basically get rid of the x squared plus 1 squared on the left, and multiplying 0 by anything on the right just still gives us 0. So we end up with minus 2x squared plus 2 is equal to 0. So 2 is equal to 2x squared. So x squared is equal to 1. So x is equal to plus or minus 1. So we worked out in the previous slide that x is equal to plus or minus 1. Thus, there are two possible points of inflection. One at x equals minus 1 and the other at x is equal to 1. But we need to check if the second derivative changes sign about or either side of each of the values of x. Let's evaluate the second derivative at x equals minus 2, 0 and 2, because these values are either side of minus 1 and 1. So the second derivative is minus 2x squared plus 2 over x squared plus 1 squared. So we're going to swap each of these x's first of all for minus 2. So subbing in minus 2 in place of both of those x's gives us minus 6 over 25, which is a negative value. We're not interested in what the number actually is, just that it's negative. Next we're going to sub in place of these x's 0. So we swap each of those x's for 0 and we get 2 over 1, which is positive. And then we sub in place of both of these x's, x is equal to 2. So we swap both of those x's for 2 and we end up with minus 6 over 25, which is negative. So we're going from negative to positive to negative. Thus, the second derivative changes about both x equals minus 1 and x equals 1. Hence, there are two points of inflection. Now remember, we were asked to find the points of inflection. And a point has an x value and a y value. So we take our two x values, which is 1 and minus 1, and we substitute them back into the original equation or the original function. So the original function was y equals the natural log of x squared plus 1. So we swap this x for 1 and minus 1. So when x is minus 1, we get the natural log of minus 1 squared plus 1, which is the natural log 2. So minus 1, natural log of 2, is 1 point of inflection. So on our x and y axis, so here's our x axis, here's our y axis, our Cartesian plane. Here we have minus 1, and the natural log of 2 is somewhere in between 0.5 and 1. It's about here. So this is approximately where our point of inflection is. And then we do the same with 1. So we get the natural log of 1 squared plus 1, which again gives us the natural log of 2. So 1 natural log of 2 is the other point of inflection, which is about here. So if we were to draw this out and see what it looks like. So our purple function g of x is the natural log of x squared plus 1. So that was the function that we were given. So that's the purple curve. And then f of x equals 2x over x squared plus 1. So the green curve, that's our derivative. And it looks like this. And marked in red are 2 points of inflection. So this is our curve, our original curve that we were given. The green curve is our derivative. We can see that the green curve has a turning point at minus 1. And so at minus 1 on our purple curve, that is a point of inflection. And we can see again that our green curve has a maximum, so a turning point, at 1, positive 1. So at 1 on our purple curve is the other point of inflection. Suppose the second derivative, d squared y dx squared, is 0 at the point c x1 y1 on the curve y equals f of x, but that the second derivative does not change sign about x equals x1. Then the curve does not have a point of inflection at c. Rather, the curve is concave upwards at c, if the second derivative is positive on both sides of c, or it is concave downwards at c, if the second derivative is negative on both sides of c. Example 2 gives an example of this situation. So here we have example 2. So f of x maps to x to the power 4, is defined for all x values elements of the real number set. So number 1, show that f double prime 0 is equal to 0. So this means if we get the second derivative of the function and we sub in 0, we get 0 as our output, i.e. that the second derivative is 0 when x is equal to 0. So when our x value is 0, the second derivative is equal to 0. So y equals f of x equals x to the power of 4. So y prime x, the first derivative, is 4x to the power of 3. So bring the 4 down in front, reduce the power by 1. And f double prime x, so the second derivative, is equal to 12x to the power of 2. So we bring the 3 down in front and reduce the power by 1. So 12x squared. So now to find f double prime of 0, we swap the x for 0. So 12 times 0 squared is 0. So we have shown that this is true. Part 2. Show that the curve y equals f of x does not have a point of inflection at 0, f of 0. So at 0, 0. So from part 1, we stated that f double prime of 0 equals 12 times 0 squared equals 0. So as f double prime minus 1 equals 12 times minus 1 squared, which is equal to 12, and f double prime of 1 equals 12 times 1 squared equals 12. So both of these are positive, 12 and 12 is positive. The second derivative does not change sign about x equals 0. So we're going from positive to 0 to positive. So it does not change sign. Hence, 0, f of 0, is equal to 0, which is equal to 0, 0, is not a point of inflection. So the reason for choosing minus 1 as an x value and 1 as another x value is because they are either side of 0. Part 3. Describe the behavior of the curve at the point 0, f of 0. As f prime 0 is equal to 0, 0, 0 is a stationary point of the curve y equals x to the power of 4. F prime minus 1 is equal to minus 4, and f prime 1 is equal to 4. So the derivative of the function with an x value of minus 1 gives a y value of minus 4, and the derivative of the function with an x value of 1 gives a y value of 4. Hence, by the first derivative test, 0, 0 is a local minimum. Also, as the second derivative is positive on both sides of 0, 0, the curve is concave upwards at this point. The curve is shown opposite. So here's the point 0, 0. It's our local minimum, and it's concave upwards. So this is our working out. So f prime x equals 4x to the power of 3. So f prime minus 1 equals 4 times minus 1 to the power of 3, which is minus 4. And f prime 1 equals 4 times 1 to the power of 3, which is 4. So we've gone from negative to 0 to positive. So therefore we have a local minimum. The alternative name for a saddle point as a horizontal line of inflection highlights the fact that as well as being a stationary point, a horizontal tangent, it is also a point of inflection. It is the only type of point that is both a stationary point and a point of inflection. Summary. Suppose the curve y equals f of x is differentiable at c x1 y1 and around c, so either side of c. We are now in a position to summarize what we can say about the features and shape of the curve based on the values of the first and second derivatives at c. So there's a good few points to go through, and it would be a good idea to know them off by heart. So, point number 1. If dy dx, the first derivative, is greater than 0 at c, the curve is increasing at c. Point 2. If dy dx, the first derivative, is less than 0 at c, the curve is decreasing at c. Point 3. If dy dx is equal to 0 at c, the curve has a stationary point at c. This could be a turning point, a local max or a local min, or it could be a saddle point. Point 4. If dy dx, the first derivative, goes from positive to 0 to negative through c, the curve has a local max at c, a local maximum. Point 5. If dy dx, the first derivative, goes from negative to 0 to positive through c, the curve has a local minimum at c. Point 6. If dy dx, the first derivative, goes from positive to 0 to positive, or from negative to 0 to negative through c, the curve has a saddle point at c. Point 7. If dy dx, the first derivative, is equal to 0, and d squared y dx squared, the second derivative, is less than 0 at c, the curve has a local maximum at c. Point 8. If dy dx, the first derivative, is equal to 0, and d squared y dx squared, the second derivative, is greater than 0 at c, the curve has a local minimum at c. Point 9. If dy dx, the first derivative, is equal to 0, and d squared y dx squared, the second derivative, is equal to 0 at c, c is a stationary point. But to determine its nature, we need to examine the sign of the first derivative on each side of c. Point 10. If d squared y dx squared, the second derivative, is greater than 0 at c, the curve is concave upwards at c. Point 11. If d squared y dx squared, the second derivative, is less than 0 at c, the curve is concave downwards at c. Point 12. If d squared y dx squared, the second derivative, is equal to 0 and changes sign at c, i.e. d squared y dx squared, the second derivative, goes from positive to 0 to negative, or from negative to 0 to positive at c, the curve has a point of inflection at c. Point 13. If d squared y dx squared, the second derivative, is equal to 0 and goes from positive to 0 to positive at c, so no change of sign, the curve is concave upwards at c. And number 14. If d squared y dx squared is equal to 0, so the second derivative is equal to 0 and goes from negative to 0 to negative at c, so there's no change of sign, the curve is concave downwards at c. Okay, so I know there's a lot of points there to remember. Some advice would be draw out a rough sketch of whatever's going on. If you're unsure what steps to use, find the first derivative, find the second derivative, investigate the sign of your value at either side of 0, choose values either side of your x and investigate what's happening and put something down on the paper. Don't leave it blank.